So the title, Computing Lower Bounds for a Polynomial Using not semi-definite programming, but geometric programming. And this is me and my co-authors, Mehdi Gassemi and Jean-Bernard Lesser. So here's sort of a summary of what I'm going to talk about. There's 3 papers, actually. The last one is just in preparation. There's a new algorithm for computing a new lower bound for a polynomial in the polynomial ring and n variables, either globally or on some sort of a constrained semi-algebraic set using geometric programming. And the thing about this bound is it's definitely typically not as good as the lower bound obtained using semi-definite programming algorithms, but it is much faster, and it does take full advantage of the sparsity of the coefficients. And it's actually quite accurate when the number of monomial terms in F is small. And finally, it works in cases where the degree is large and the number of variables is large. And these are cases where semi-definite programming just breaks down. It just doesn't work. Eh? So our bound still gives you something. So the algorithm was developed first in the case of global optimization on real n space by Gassemi and myself, and it's already appeared. And then later on, the method was modified to handle optimization on what I call hyperellipsoids, which are sort of like television screens or something, okay? Sets of this form, where D is any even integer bigger than or equal to 2, bigger than or equal to the degree of F. So you could optimize it, a polynomial F on such a set, which is, of course, a compact semi-algebraic set. Eh? And this paper still hasn't appeared. It's Gassemi, Lesser, and myself. Well, I guess it's almost appeared now, but maybe officially not. And then most recently, there's a third paper where Gassemi and I have attempted to modify the method to handle optimization on more general constraint sets of this form. Not all of them, but many of them, okay? Where the G here, bold G, is an M tuple of polynomials, okay? And that's, well, we're still working on it. So the outline of the talk is, so tell you what geometric programming is in case you don't know. I didn't know until I started this business. Theoretical background, then a lower bound on, so this is global optimization section. And then very briefly, I'll talk about the general situation where you're optimizing on this constrained set of this form. And then finally, I'll spend more time on the hyperellipsoid where you get more definitive results, I guess. What happened? Okay. So I remember Gassemi and I were working on this stuff way back at the beginning, and we got something. And Gassemi said, you know, this is a geometric program. And I said, what's a geometric program? So I found out, okay. So a geometric program, it's a, okay, so a function, I have to define monomial. So a monomial function is just defined on the positive n tuples of positive reals. So it's a monomial like this. So the xi's are positive reals. The ai's are constants, but they can be any real numbers. They don't have to be integers. They don't have to be positive, the ai's. The coefficient has to be positive. So that's just, well, that's slightly more general than what we usually think of as a monomial. We'll call that a monomial function. And if you have a sum of monomial functions of this sort, so that's a function like this where the CI's are strictly positive, these are monomials, it's called a polynomial. So it's important here that the coefficients are positive, strictly positive. So then an optimization problem of this form where you want to minimize such a thing subject to some inequalities and some equalities where the ph's are polynomials and the c's are monomials. That's a geometric program. Well, then you have the feasibility set, which is the subset of n tuples of positive reals defined by these constraints. That's the feasibility set of the geometric program. And, well, as usual, this is called the objective function of the geometric program. And the output is the minimum, or more precisely, the infimum of this, where the x runs through the feasible set. Right? And of course, if the feasible set is empty, the convention is that the output is plus infinity. And there's a standard reference here, this tutorial on geometric programming by Boyd et al. So that's all I'm going to say about geometric programming. Theoretical background, well, there's a page of notation and then there's a result. Right? So the page of notation, which we use all the way. So we fix an even integer bigger than or equal to 2, and we look at n tuples of non-negative integers whose norm is less than or equal to d, where the norm is just the sum of the entries. Okay, and when I write 0, I mean this n tuple. And when I write epsilon I, I mean this n tuple, where the epsilon ij is d, if I is j, and epsilon ij is 0 otherwise. So this has just got one non-zero entry, which is d, okay? That picks d. And now if you have a polynomial of degree less than or equal to d, I write it this way. This is just the coefficients, these are the monomials. Okay, so an omega of f, it's kind of technical. So it's all the non-zero, it's all the alphas where the f alpha is not 0, except you throw away these guys. So in other words, you can write the f this way, where the f0 is just the f0. It's just f evaluated at 0. That's what the f0 is. And this is just the coefficient of x to the x sub I to the d, right? That's what this is. And you just write that way, okay? So when I never write this anymore. I just write this. And I never write this anymore. I just write this. So the f breaks up. These are just the other terms. Eh? That's all. And so this, what happened? So these are just the other terms. You have these terms, and then you have these other terms. And then the delta of f is, well, you throw away the ones that are squares. So you keep the ones that are not squares. Some of these monomials will be squares, right? Perfect squares. And you throw those away. Right? So that's what delta of f is. And then you have this, which is the elements in delta of f where the norm of alpha is less than d. And you have this, it's the elements in delta of f where the norm of f is d. And mostly we're interested in the case where the degree of f is exactly d, right? And of course d is even, right? We're assuming d is even. So that's our notation. And unfortunately, you're not going to see it, okay, anymore, because it's on the previous page. So here's, I guess, the main theorem. If you have it's a form now. That means it's homogeneous polynomial of even degree, and we're assuming the even degree is exactly d, and d is bigger than or equal to 2. And so I can use all this notation I had before. So what do you get? You get a sufficient condition for f to be a sum of squares. It's not necessary, it's just sufficient. Is that there exist non-negative real numbers, z alpha I. So it's sort of a matrix of numbers, right? Because alpha's running through delta of f, and the I is going, it's the number of variables, or I is going from 1 to n, and it's the number of variables. If there exists such an array of non-negative numbers satisfying these three conditions, eh? And there's some shorthand, oops. There's some shorthand. Yeah, here, this notation is explained. This is just this product. So this is a condition about when you fix the I and take the sum over the alphas, right? And that has to work for each fixed I. This is a condition where you fix the alpha and you take these products over each I, right? So in one you're fixing the I and adding up over the alpha, and the other you're doing the other way around, except you're multiplying instead of adding. Okay, and yeah, actually, if you have these three conditions holding, it actually means that f is going to be a sum of binomial squares, not just a sum of squares. It's going to be a sum of squares of this special form, which we call binomial squares. So I don't want to say anything about the proof of this theorem, except you can deduce it from a recent result of Fidalgo and Kovacic. And in turn, this result of Fidalgo and Kovacic, you can deduce from an old result of Hurwitz from a long time ago, 1891. Or you can look at this paper of ours, and there's a very short self-contained proof. It's not such a complicated thing. I mean, this looks really mysterious, but it's not complicated. So we apply this. That's our theory. We apply. And we get the following result as a corollary. So again, you have an even integer bigger than or equal to 2, and you've got a polynomial. What am I doing wrong here? Pushing my wrong button. I've got a polynomial. Now it's not a form, it's a polynomial of degree less than or equal to d. And you let rho of f be the optimum value of this program, where for every alpha, these unknowns, I guess that was also on the previous slide. These unknowns have to satisfy this condition, right? Condition 1. So now condition 1 is still there, except I'm writing it down here, right? These are 0 if and only if. So you want this to be 0 if and only if the alpha i's are 0. Then you can say this thing is a sum of squares. Actually, it's a sum of binomial squares, which means this quantity here, which is defined to be this, is a lower bound for f on Rn. So that's how we get our lower bound. It's a really sort of silly lower bound. And the thing to notice is that if these are positive, strictly positive, then this program is a geometric program. And slightly more generally, I mean, sometimes this condition just vanishes because this is 0 and this is also 0, and then it's just saying 0 is less than or equal to 0, and you can throw it away. So that's the case where this happens, and it's also a geometric program in that case. And in all the remaining cases, it's not a geometric program, but who cares? Because you already know what it's going to be. You can compute it, okay? If you're not in those two cases, the feasible set is empty, and the optimum here is plus infinity. And so when you work out this thing, you get minus infinity, which doesn't tell you any. It's not much of a lower bound, right? It's a lower bound. So in all the interesting cases, it's a geometric program. And, well, the way I've set it up here, this thing depends on how we choose the d. And it's really defined for the degree of f less than or equal to d. But we're really only interested in the case where f has even degree d. That's the case where we're interested. Because in the remaining cases, it's really trivial. I explain how it's trivial. I want to define this for the degree of f less than or equal to d because I need it later. But actually, we're only interested in the case where the degree of f is d, because otherwise this is sort of a trivial thing. So now, what do I want to say? Well, okay, then there's the semi-definite programming. I guess this is the first Lasserre approximation, right? You just take the infimum, well, there's only one here because it's global. You take the infimum of all r's such that f minus r is the sum of squares. Call that FSOS, and then you have what you're really trying to compute is the infimum of f of x where x runs in R through Rn. This is what you really want to compute. This is what you can compute using semi-definite programming, and this other thing you can compute using geometric programming. And you can, well, it's more or less clear. You get these. This thing is never better than, it's never better. It could be equal, but it could be worse. So it's got other advantages. Anyway, here's some examples. N equals 3, d equals 6. They're all equal in this example. I mean, of course, you can always find an example where good things happen, right? But they're all equal in this case. Here's another example. Also 3 variables, degree 6. Here, this thing is a little bit bigger, and these two are equal. Okay, and then this third example, which is basically the same as the example 2, except I've added an extra term, x squared. And now they're all three of them are different. It's this is smaller than this, which is smaller than this. Well, there's just some examples to show how it works. Computation times. Computation times. Now, the n is the number of variables. D is the degree. These are computation. Oh, and this is omega f. That's basically the number of terms, right, in f. And so as long as this number of terms isn't too big, you can really compute this thing really fast. This is for computing FGP. Well, I mean, this one takes an hour, but and these are cases where most of these cases you could not compute using semi-definite programming. Just wouldn't. It would break down. So the main advantage of this over this is that in the case of many variables in high degree, you can actually compute the FGP, whereas you can't compute the FSOS. Well, I mean, especially if you have a sparse polynomial, right? It helps if this is not too big. Eh? And also the accuracy of this thing is not too bad, especially when this set is not too big. Eh? And I've got a really, I mean, this is a stupid example, right? But this is a stupid example. You try to compute this using semi-definite programming, it crashes. I mean, it just doesn't. It's got degree 40. I mean, it's not going to work. 3 variables, degree 40. You try to compute using geometric programming, it takes some fraction of a second, and gives you the right answer, the exact answer. So there's something going on here, right? This is an extreme example because there's just one element in the omega of f, right? There's one term. But there is something to this. No, okay, that's the end of a part. And this, I guess I want to do really fast because I want to get to the next part. So now I start with the case where I've got polynomial f and a bunch of constraint polynomials, g1 up to gm. And I talk about this set as before, right? This basic closed semi-algebraic set. And you want to optimize f on this set. And yeah, so you got to say what d is. So you take d to be the least even integer bigger than or equal to the maximum of 2 and all the degrees of these. Okay. And you sort of want to generalize what we did before, except we're doing it for constrained optimization. And so the idea is the following. You look at this new polynomial, which depends on some parameters, which are non-negative real numbers. You've got m parameters. M is the number of constraints there. So if we use theorem 5.1, this gadget here is a lower bound for this polynomial on Rn. And because f is bigger than or equal to g lambda on kg, it follows that this thing is actually a lower bound for f on kg. So then if you take the supremum of all these things, that's a lower bound for f on kg. Now, it would be nice if you could compute that thing by geometric programming. You can compute each one of these by geometric programming. But that doesn't mean you can compute the supremum. But sometimes you can. So sometimes this thing is computable. And in our paper that we're working on now, we explain cases where this is computable by geometric programming. And also, and I guess this is important, even if it's not computable by geometric programming, this thing may not be computable by geometric programming, but we can relax it a little bit sometimes to find something that is computable by geometric programming, a little bit smaller, okay? So anyway, this is coming up in this paper that we're preparing now. So now let's go to the hyperellipsoid. So I'm just going to deal with this special case where the number of constraints is 1, and the G1 is just this hyperellipsoid thing. So I'm going to write Bm for the Kg, and now your G lambda looks like this. Say there's just one term here. So lambda is just a single non-negative real. And we'll denote this lower bound. Instead of writing this lower bound this way, we're going to write it this way, FGPM. And of course, the reason we do that, I guess, is because it is computable by geometric programming. I mean, there's this theorem that you can actually compute this in this special case. This thing, which is this thing, is computable by geometric programming. Now, when you're doing this, it depends on d. This quantity you get depends on d. The only restriction is that d is even and bigger than or equal to 2 and bigger than or equal to the degree of f. And another important thing here is that unlike the other lower bound, the global lower bound, this one is also of interest when the degree of f is less than d. This thing is really only interesting when the degree of f is equal to d. This thing is interesting, very interesting, when the degree of f is less than d. And I guess these are just some of the things you can show. I'm not going to talk about that. And you can also get these inequalities as before, where this is, I guess, the kth Lasserre relaxation. So the dth one is more or less the smallest one that you'd want to use. And this is actually the infimum of f on this hyperellipsoid. So you can show these things just as before. And I guess I'm just about done here. Here's just some examples. Well, this is a stupid example where this thing ends up being equal to this thing. I mean, it's not usually the case, right? Here's an example where this thing's a little bit less than this thing. I mean, I've done it for various m's, right? M equals 1, m equals 10, m equals 10 squared. Yeah, and you can also compute this thing in cases where you just cannot compute this. So here's an example. I think it's got degree 39, and you take d equals 40, and you can compute, I don't know how accurate this is, how close it is to the real minimum, because it's very hard to compute the real minimum, and that's why I'm interested in this stuff, right? You want to get the real minimum, you go to Maple or something, or it will give you, it'll try to find some local minimum or something. So I don't know how close this is. I don't know how close this is to the true minimum. And I don't know how to decide. I mean, maybe somebody can tell me if there's a way. But I think if there's a way, we wouldn't be worried about the semi-definite programming, right? Okay, yeah, this last section won't take too long, I guess. Something about the quality of this geometric programming bound. You know, how good is it? Eh? So the thing to observe is that if you take minus f sub star m, that's the minimum of f on minus f on Bm. So that if you put a minus in front of it, that's the maximum, right, of f on Bm. So then when you work out this ratio, it's sort of your estimate for the maximum minus your estimate for the minimum. Eh? Your f is sitting here somewhere, and you've got an estimate for the maximum, estimate for the minimum, and the difference, you know, this distance, that's the numerator. And the denominator is the same thing, only your SDP is better, so it's going to be smaller, right? So for the SDP, this number here is always going to be less than this, so the ratio is going to be bigger than or equal to 0. And of course, if it's close to, bigger than or equal to 1. And if it's close to 1, this means you're pretty accurate, right? And if it's far from 1, well, you're not so good. Eh? So that's, I guess I can go to the next page. You see that T is the number, so this is the average value of R for various N, D, and T. T is the number of terms in F. N is the number of variables. D is D is just the D, right? R is that ratio. Well, no, you're working out the average value of this ratio over, I don't know, maybe it was 10 polynomials chosen at random or something. And you see, well, I mean, that's not so good. That says for 3 variables, degree 6, if you have just 5 terms in F, the error is 23.8%. I mean, this is not bad, but it's, you know. If you fix the D and the T and increase the N, it gets better. It's getting better, right? This is bigger than this is bigger than this. This is bigger than this is bigger than this. If you fix the D and the T and you increase the N, the approximation gets better. Of course, if you fix the n and the d, and you increase the t, it gets worse. Eh? And in fact, it gets very bad after a while if t is too big. So, okay, I guess that's all I want to say. I don't know if we have time for questions or not. I guess, yes?
So that thing you called a hyperellipsoid,
Yeah.
it looks like a ball for the Minkowski LP metric.
Yeah, it does, doesn't it? Yeah.
Is that the motivation that it has applications in metric embeddings or metric spaces or something?
I don't think we ever thought about it that way. I mean, I guess I knew. I mean, as soon as I looked at it, I saw something, yeah. But as far as the application, I don't know. I guess originally we looked at this thing and we thought, well, okay, sometimes you can get a lower bound for f. If you know the minimum occurs in some big ball, you just minimize on the ball, you might get a better minimum that way. That was our original idea. And of course that works, I mean. Okay. So if you have any more questions, you can ask me during the break, okay? So this goes on until what? How long is the break? Half hour? I'm not a very good...
4 o'clock.
4 o'clock. So half hour, I guess, yeah.